Hello and welcome to video 1 on equilibrium, Zumdahl chapter 13, equilibrium. I'll start off by providing a strong definition for chemical equilibrium, what it is and what it isn't. It's tempting to see the word equal and think of equalities with equilibrium. In reality, the only thing that's equal in equilibrium, are the forward and reverse reaction rates of a system. Okay, and it's important to note we mean rate, the speed at which products are made and the speed with which reactants are made. In a dynamic equilibrium, which is what all chemical equilibria are, you're always making reactants and products. It never stops happening. Even when the reaction is perceptibly done at equilibrium, products are still being made and reactants are still being made. The reason it's perceptibly done is because you are no longer making more of one or the other. You're simply replacing one with the other, and vice versa at the same time. And so you have a constant concentration of reactants and products, all the while you're seeing one reactant become a product and one product become a reactant. Then when that rate's the same, you have equilibrium. Okay, if you allow a system to be undisturbed and not undergo any forces external, any changes external, then it will come to equilibrium all by itself. This is a graphic showing the concentrations of reactants, carbon monoxide and water, and products, carbon dioxide and hydrogen. You note that at the beginning of the reaction you have all reactants, no product, and we see that from our kinetics learning, we see our initial rates are rather steep, but as products start forming, we see that the rate of consumption slow, and we see the rate of production slow. It's pretty steep at first, but then it flattens out, and eventually we reach a point we hadn't talked about yet where we don't see any more change in concentration. This is equilibrium. Although we have a zero change in concentration, we are still producing reactants and products just at the same rate. So let's look at this in terms of rate. Again, initially all reactants, no products. So our rate of forward reaction, reactants becoming products, is very large. And that slows as products form. And as products form, we see that rate increase and then slow. And then eventually we see that their rates become the same. Okay, so again, this is rates compared, forward reaction, reverse reaction, and then we find that at equilibrium those rates are identical. So the law of mass action helps us describe equilibrium. We take a balanced chemical reaction where this lowercase letter is the coefficient and the uppercase letter is the substances involved in the reactions. We use the symbol Kc to symbolize the constant this product creates. We take each product to the power of its coefficient divided by each reactant to the power of its coefficient. And they're all multiplied together. And what that yields is what's called the equilibrium constant for that process at that temperature. Okay. Now these values we would plug and chug in this would have to be at equilibrium for this to be true. When we see brackets, this implies a concentration in moles per liter. Usually this is for aqueous solutions, but it can be done for gases if you know this information. When a system is not at equilibrium, we do the exact same process to help determine what the system's likely next move is going to be. When we know our system's not at equilibrium, we do the same mathematical process. We call that, though, the reaction quotient Q sub C. And again, that C is in terms of concentrations. Sometimes we'll see it K sub C, K, and sometimes KEQ. These are all used interchangeably. Kc is the most descriptive of the three. If we take a sample chemical reaction, in this case ammonia and oxygen forming nitrogen dioxide and water, we notice that we are applying what we saw with the law of mass action, where our products are over reactants to the power of their coefficients. If you know concentrations for each of one of these equilibrium values, then you can calculate Kc directly. It's important to note that the only way to influence K is with temperature change. When you change temperature, you change equilibrium's position, and so K will change. You cannot change K with concentration changes or pressure changes. If you were to reverse a reaction, to analyze a reaction from the reverse, in other words, to analyze it AB making CD, you would essentially invert your Kc value to determine the equilibrium constant, and we'll call that Kc prime. Okay, and note that we have products over reactants for the reverse reaction. If we manipulate the quantities of the reaction, we could multiply all the coefficients by an integer or a fraction, and mathematically the impact there is it simply changes k to the power of that impact on the coefficient. The impact here is that if we're, say we're given fractions instead of whole numbers as exponents, that's going to impact k in an obvious fashion, because if you your the fractions that you placed into your coefficients would impact your exponents on your concentrations. So ultimately, whatever value you multiply each fraction by, whatever value you multiply each coefficient by is placed as an exponent on your k value. That's often called k double prime. For multi-step processes, it's fairly straightforward what has to happen to determine the overall k for a multi-step process. For each individual reaction, we simply multiply the k values for those sub-reactions to get the overall k for the sum total of those reactions. And this could be applied in a situation like a reaction mechanism where you had multiple steps and happen to be given k values, or perhaps a thermodynamic system, thermochemical system where a multi-step reaction was given to you and k values were also given. The units for k are a thing, however they're typically not expressed. They can be determined simply by following your units through the k expression, but generally we don't see them used. We might have a few vague questions about them, but nothing that should be considered of consequence. Sometimes we use the word equilibrium position. It simply describes a set of equilibrium concentrations for a certain chemical or certain substance or process. It depends on initial concentrations. Remember, Kc doesn't and will not change unless temperature changes. We can also describe equilibrium in terms of pressures, and what we're going to note here is really the symbolism more than anything else. It's the same exact thing as it is for concentrations, moles per liter, but were your equilibrium values for a gaseous system given to you in atmospheres, then this is the symbology you should use. Again, it's going to be the value to the power of its coefficient for the balanced reaction. It's just that you need to write P for the word partial pressure to the subscript of the identity of the compound. So P sub O2, P sub CO2 to the power of their coefficient. And just note that you've got, instead of brackets, parentheses. College Board enforces pretty aggressively. If you have atmospheres and pressure for your equilibrium values, you need to use parentheses with a P sub, the identity of your substance. Again, generally speaking in chemistry, we'll see most values given in atmospheres, especially when dealing with thermodynamic equilibrium systems, because we often will use R, and people tend to stick to the atmosphere's SI unit. The Kc relationship with Kp is pretty straightforward. This is a formula that allows you to convert between the two. Kp is equal to Kc times RT. This is the universal gas constant R in terms of atmospheres, temperature in Kelvin, and then times to the power of delta N. And delta N is the number of moles of gas product minus the number of moles of gas reactant in the balanced reaction. And so, provided this is an integer, a non-zero integer, you're going to have a value for Kp that's a little different from Kc. If you have the same number of moles gas reactant and product, then you will have Kc equal to Kp. It's important to note that we can only use gases and aqueous solutions to describe equilibrium, and the reason for that is solids and liquids cannot change concentrations by any means without changing the identity of the substance. So if we see a solid or a liquid in a balanced chemical equation, it can't impact equilibrium because it can't change. Okay, those concentrations are essentially their densities, their intensive properties of the substance. Therefore, they don't change. Gas pressures change and therefore can influence equilibrium. aqueous solution concentrations can change and can influence equilibrium. So when you write an equilibrium expression for a substance that for a reaction that contains solids and liquids, you simply omit them or ignore them in your equilibrium expression. So for the decomposition of calcium carbonate solid, we would have a K expression that basically is K sub C is equal to the concentration of CO2, and that is all. Or the partial pressure of CO2 if given a gas in atmospheres. So interpreting K values is quite important, and it's simply mathematical association here. So you should notice that since we're dealing with an expression that's products over reactants, when K is a large number, that typically means that equilibrium lies to the right, which means that you're going to have mostly products in your system at equilibrium. If it's less than 1, then equilibrium lies to the left, which means we'll have mostly reactants at equilibrium. It's important to understand that the kinetics of this and equilibrium are not directly related. The time needed to reach equilibrium and the size of K are not directly related, so you can't associate the rapidity or how fast it happens with the size of K. It does not imply a kinetically fast process. K values can not always be compared because of stoichiometry is different. So if you have two different chemical processes in which you have different coefficients, K values don't necessarily mean a whole lot when simply looking at the system unless you have a stoichiometrically identical pair of processes. Like, for example, hydrochloric acid decomposes with stoichiometry the same as hydrofluoric acid decomposing. So those can be compared pretty readily. The K values for those two processes can be compared. But it's harder to do that when the reactions are not similar. So this is a nice graphic that illustrates the logic of K values. We see that K's between 10 to the negative third and 10 to the third tend to contain systems that have, at equilibrium, some distribution of reactants and products. If the K is larger than 10 to the third, you typically don't have much reactant in the system. 10 to the negative third, you don't have much product in the system. This is a sample problem that's in the notes, and I just wanted to go through it. It sets you up with a balanced reaction, which is the first thing you need when dealing with equilibrium. And then we're given some information about a system that was mixed and allowed to come to equilibrium. And these are the equilibrium concentrations. And it asks us to find the value for K. In order to do that, we need to write the equilibrium expression first, and that allows us to see mathematically what we need to do. And then we see its products over reactants to the power of the coefficients given to us in the balanced reaction. And then we can simply insert those variables into the equation and calculate a K value. Notice how omitted units here. We have 3 moles of reactants and products and 2 moles of reactants, so we would see a unit on K in this particular example, but we aren't going to bother with it. We can also take that same reaction and then determine a K prime, or the K value for the reverse reaction, by simply inverting the K we got from the first set of operations. And there's that. We can also manipulate the coefficients by multiplying them all by 2, which essentially we take that factor we multiplied each coefficient by and place it as an exponent on K, which gives us this value. And we can also find Kp using the equation that converts between Kc and Kp. But keep in mind I talked about there are 3 moles of gas on the product side and 2 moles of gas on the reactant side, so our delta M is 1. Go back to the balanced reaction and take a look at that to confirm that you see why that is. And that gives us this Kp. So we saw 3 impacts on the K value there. And finally, quick word about reaction quotient. Reaction quotient we know how to calculate. We can use the information about a non-equilibrium position, calculate a Q, and then compare it to K. And because we understand how K is calculated, products over reactants, we can make an assumption about what our system will do to reach equilibrium. Because keep in mind, all systems left alone will return to equilibrium without any outside force. And so we'll calculate a Q value to do that. If K happen to equal Q, then we're at equilibrium. There's no shift. Nothing will happen to our system. If Q is larger than K, that implies we have an overabundance of products and our system will make reactants. If Q is smaller than K, we have an overabundance of reactants. We can expect our system to make products. And that is where we'll stop for this video. Stay tuned for more.